In this video, we share our research on crowdsourcing and evaluating concept-driven explanations of machine learning models. Machine learning algorithms perform critical decision-making activities in domains like healthcare, finance, and security. For humans to rely on these decisions, algorithms should be both accurate and transparent, and should be able to explain their decisions. Explanations of machine decisions often use importance of low-level data features like pixels in an image or words in a text. For instance, an explanation might suggest that to classify the image as a tiger, a set of pixels corresponding to the tiger were important to the algorithm. While these low-level data features are faithful to the machine, they may be hard for humans to understand. Humans instead operate on higher-level features like concepts. Concepts are abstract mental representations that help us make sense of the world. They are the mental representations of classes or categories of things which help individuals reason and differentiate entities. For instance, black stripes on a yellow surface may correspond to a tiger. The choice of features, low-level or high-level, can alter the language of the explanations. In our work, we ask, how does this language of explanations impact the interpretability of AI models? In this research, we explored two axes that characterize concept-based explanations: granularity and context, and their impact on human interpretability of the model. Granularity refers to the level of detail provided by the data features used to explain the decision. Low-level details, like importance of each pixel in the image for a given class, provide a high degree of detail with regards to models' mathematical representations, and hence are fine-grained. High-level features, like parts of an object in an image, offer specific and well-defined information structure and hence are coarse. Different degrees of detail affect the amount of information that can be derived from explanations. Context, on the other hand, refers to the breadth of data instances used to explain the model's general behavior, and the method used to display any related instances. Context in the explanation provides information regarding how the model processes similar data instances. An explanation that only refers to one data instance is described as context-less. An explanation may also describe the local context, when information from only select highly similar samples is presented, or global context, when information from all similarly classified data instances is presented. Together, granularity of data features and context of data instances provide a conceptual mapping necessary to correctly interpret a concept-based explanation. Before we investigated how these axes influence interpretability, we need a mechanism to reliably generate concept-based explanations. While it is possible to algorithmically generate concept-based explanations to some extent, these algorithms are not always reliable and difficult to train. Therefore, we designed a crowdsourcing methodology that captures conceptual information about a dataset from direct human feedback. Our concept elicitation pipeline is made up of 4 stages. We first select seed data samples representative of the dataset. A concept elicitation task helps crowd workers outline the concepts corresponding to these seed data instances. 309 unique workers elicited 9,000 concepts from 149 data instances. The elicited concepts were then passed through a validation task that were validated by 322 unique workers. Finally, we aggregated these concepts across the dataset to create a set of unique concepts representing the dataset. While in this experiment, we primarily tested this pipeline on images. This pipeline also works with text corpora. We then use these concepts to design explanations for a highly performant deep learning image classification model. We created several explanations varying on different levels of granularity and context. While granularity was represented using a heat map, we used a bar chart to present context. With 4 conditions across granularity and 3 conditions across context scales, we explored 12 different explanation prototypes across 91 data samples. We designed our study to identify how well these explanations helped people estimate the predictability of the model. During evaluation, we observed several interesting themes. Firstly, our study demonstrated that model explanations which provide contextual information, grounded in human-friendly conceptual language, help to make models more interpretable. And while context helps, it needs to be presented in an actionable way. For instance, using contextual information as a mechanism to spot-check poorly performing instances versus auditing all instances for a given class. We also observed granularity requires some fine-tuning before we can reliably use it. Pixel-to-pixel heat maps were considered reliable, even if they require a high degree of information processing. And when we provided well-defined regions as explanations, self-reported confidence ratings and model predictability performance scores went down. We also observed that concept-based explanations of both true and false positives required a different level of information. Furthermore, while one would expect confidence in the model to decrease when participants see incorrect behavior, we were surprised to see a similar drop in their perceived quality of the explanation itself that disrupted their ability to estimate model performance. To explore more detailed findings, please check out our paper. Thank you for your time.